2. 2, c sub 2. You see it now? X minus a to the 1. And that gives us this one. And then the next one, so on and so forth. So that's pretty nice. Cool. We have a formula. But does anyone, yeah, do y'all see something pretty actually amazing / cool? That if you just, instead of writing it all out, if I give you a power series like this and ask you to take the derivative, what really happened? The n popped out, and then we reduced the power by 1. That's the power rule, isn't it? With one exception. There's one other thing that happened that you must not forget. It could really haunt you later. The index changes. Right? It went from 0 to 1. Yes?
So if you take the second derivative with the index change to 2?
Pardon me?
With the index change to 2, if you take the second
If so, yeah, I wonder what would happen if you took the derivative again. It would go to 2 the next time through. Yeah. What we would normally do, though, is after we take the derivative, we would switch our n back to 0, but I haven't shown you how to do that yet. And then get everything back to like a general power series, and then that's pretty neat. While I've got it on the board, I wonder if integration works the same way. All right, so what if I asked you to find the antiderivative of f of x dx? Now, what happens every time we take a general antiderivative? An indefinite integral. You always get plus c, right? You always had that plus c at the end that your instructor sometimes got mad when you forgot it. Or maybe they didn't care. But you always had the plus c, right? So you're supposed to find the antiderivative and at the very end say plus c. We can't do that. The reason we can't do it is because our answer is going to be infinite, isn't it? So I'm going to have plus ... And so I can't really put a c at the end. So what I'm going to do is instead put the c at the beginning. Okay? So I'm going to start by saying c. Plus, now let's start taking the antiderivative of this, piece by piece. What is the antiderivative of a constant with respect to x? The constant times x, right? What's the antiderivative of this? C1, did you say over 2? Yes. So you would have, I'm going to write a little different. I'm going to put 1/2 C1 instead of C1 over 2, and then x minus a squared. Let's just double check that. For the antiderivative of this, is it this? We'll check it. Take the derivative. What's the derivative of this? 2 comes out, right? Cancels out. You have C1, this to the first power. What's this? What would the next one be? 1/3 C2 x minus a to the third power. Next one. 1/4 c sub 3 x minus a to the fourth plus ... forever. It's looking pretty nice so far. I need to try and come up with a formula now. Yes?
You have the minus a on the COX.
I do have the minus a. What?
On the second one? For everyone that has an x, you have x minus a, but on that
I have x minus a, x minus a, x minus a. Is that what you're saying?
Why would you have it on that one?
Why do I or don't I? Well, because the antiderivative of a constant is just, right? Like if this was just 5, right? The antiderivative of that is 5x, right? But I think you're seeing a little bit ahead. We have a little bit of a problem with this one, because if we try and come up with a formula. Here's my formula so far. I know that this is equal to, I forgot to write the c. C plus, right? Formula, let's see. Can you create all this with your series formula?
You can, starting at 1/2.
Okay, so I could start the formula here, couldn't I? Because from here on, they all look the same, right? Yeah? Okay, I'm going to write something down here, and I think you're going to maybe like this once I'm finished explaining what's going on. But instead of moving down, I'm just going to write it above this. Do you agree or not that this is equal to C plus C0 x minus a plus 1/2 C1 x minus a squared plus 1/3 C sub 2 x minus a cubed plus blah, 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 blah. So do you see what I actually threw in here? I changed the x to x minus a. Why is that okay?
Because the A is equal to 0.
Have a power.
We don't know that a is 0. We don't know. If a is not 0, those aren't the same.
Because we're going to infinity anyway, so it should be.
It's not quite the infinity.
Is it because the A doesn't have a power right there, and so because you have a constant, it kind
Okay, elaborate.
of it doesn't shift it enough to really matter?
When we say that our answer is this plus a constant, doesn't that mean like we don't know what this constant is? It gives you like a family of functions. They're all within a constant of each other. That's right. So if I sit here and I say, if I were to multiply this back through, what would my first term be? C sub 0x, which is this, right? My next one would be what? C sub 0 times negative a? That's a constant. And so that constant does not matter because I'm adding a constant that I don't even know. Right? So by doing x minus a, it actually has 0 impact on the answer. But I add it so that my formula looks good. That's kind of clever, right? All right, so if we do that, what's my formula? Sum, where do you want to start? Let's try and start it at 0. Well, what about all these numbers out front? I need to start out with 1 over 1, then 1 over 2, then 1 over 3, then 1 over 4, but I'm starting at n equals 0, so 1 over n plus 1, right? That should give me the numbers, 1 over 1, 1 over 2, 1 over 3, 1 over 4, agree? Okay, how about the c subs? C sub, just n, because if I start at 0, I get 0, then 1, then 2, then 3, yeah? X minus a to the, I want to start at 1, well, sorry, I want to start at 1, then 2, then 3, then 4, so n plus 1. Right? And do you see how this formula, right here, we could have gotten this formula by just integrating this formula? Kind of like when we were doing these, when we integrated that, we said, okay, we're going to need a 1/3 out here, right? And then that power is going to change to 3. Here, we need, well, oh, I don't have it here. Oh, here. Here, to integrate this, we need a 1/4 out front, and then that power goes up. So if I want to integrate this, I need a 1 over n plus 1 out front, and that goes to n plus 1. This time, though, the index does not change. It's at 0. So we may differentiate power series term by term, and we may integrate power series term by term. Very nice. This will be maybe our last example of the day. Express f of x equals 1 over 1 minus x, that quantity squared, as a power series. I have a packet of a bunch of work from students here. If you're wanting to get some of your work back, I'm going to leave it on this table. After class, just come by and grab it. And I'm going to pass the sign-in sheet around. I know it's been a while since I've done this. It's the 20th, right? Yeah, just sign in on the 19th. Fiesta. All right. What are you thinking here? Looks a lot like this, right? Like that thing we needed? But it doesn't have the square. This doesn't have the squared on it. So there's actually a couple of approaches that you could try on this one. But all of them are going to be a little bit problematic. So one suggestion that a student of mine earlier today had was this. Why don't we break this up into two like this? Isn't that what that is up there? And then come up with the power series for this and the power series for this. And then multiply them together. Yes and no. Yes, we could. No, I haven't shown you how to multiply power series, and that's coming up, all right? Instead, I want it to be done a different way. See if you can figure out. And I'll give you a hint. It has something to do with differentiation or integration. You know what my daughter told me last night? She's 7 years old. She said, "Daddy, I know algebra now." I said, "What? Really? Okay, what did you learn?" She said, "A plus B is 16." I was like, "Okay." If it was just that simple. Right? Nobody sees? These are related to each other. I'm trying to figure out if you can figure out the relationship between the two.
You rewrite it as the negative 2?
Rewrite that one up there. You could rewrite it, yeah, as 1 minus x to the negative 2. That is that, yes. I'm trying to see if you can figure out how this one and this one are related to each other. You're on the right track. I'm just...
Take the derivative of that, then it would...
Okay, if you take the derivative of this, what do you get? Maybe I can help you. This is the same thing I just had up here, right? This is 1 over 1 minus x. What's the derivative of this? Negative 1 comes out. 1 minus x raised to the negative 2, but then chain rule. Derivative, what's inside? Negative 1, right? Because it's a negative x. The negative and the negative cancel, and what do you get? 1 minus x and negative 2, which is this, which is that. Yeah? So, this, because we are somewhat good when it comes to derivatives, we understand that this is actually just the derivative with respect to x of this. Do you agree with that equation? The left side is equal to the derivative of that right. Now, the 1 over 1 minus x, this, you know the power series for it, don't you? So I'm going to say that that's equal to the derivative with respect to x of this power series. And the power series for that's just this, isn't it? Right? That's the power series for that one. And we just learned how to take the derivative of a power series. All you have to do is take that n, drop it down, subtract 1, and change the n to 1. Right? So this should be, so I'm actually taking the derivative now. A new series, n equals 1 to infinity, of n times x to the n minus 1. And if you want to know what that looks like, just start plugging in numbers. 1, what would you get if you plug in 1? Just 1. Plus, what happens when you plug in 2? 2x. 3? 3x squared. 4x cubed. So we wanted to know what the power series for that was? Here's what it is. Now, when is it valid? When is that actually valid? Like, when can I actually convert that to this? So long as absolute value of x is less than 1. Why did I use x? Because that's what was here, right? It wasn't anything weird. It was just x. All right. One last thing, and then we can wrap it up. When we write power series as an answer, like this would have been our answer, right? This is also an answer. If you actually write the terms out, this is a good answer also. But in a power series coming up next week, we're going to be trying to combine these together, and we're going to want them to all start at 0, or all at least start at the same place. So can I create this same series with the new formula that starts at 0 instead of 1? Yeah, we can. Let me show you the general rule of how to do it, okay? So what I'm about to show you is what we call shifting our index. So shifting the index. So I want you to look at what we have. We have in our index n equals 1, right? We want n equals 0. Okay, we want to shift this starting point from 1 to 0. So your instinct might tell you, well, subtract 1 or do something like that, but here's what I'm going to do. Here's the way I like to teach it. All you do is you try and rewrite this equation. You're allowed to change this side of the equation to whatever you want. But what I want is at the end to be able to get 0 here on the right side. So what would I have to change in order to make that a 0 on the right? I would need a 1 over here on the left side, a plus 1 on that side so I could subtract it on both sides. So what I'm going to do is I'm going to change the n to an n plus 1 equals 1. Now if I write this, if I replace the n with n plus 1 and then solve for n, won't I get n is 0? So the key to shifting your index from n equals 1 to n equals 0 is to make this change. Replace n with n plus 1. Okay, that's how we do it. Replace n with n plus 1. So what I'd like for you to do is go back to this formula and replace all your n's with n plus 1s. Let's see what happens. This becomes n plus 1 equals 1. You're allowed to do this as long as you do it everywhere in the formula. All right, so I replace the n with n plus 1. I replace that n with n plus 1. And I replace the n up here with n plus 1 and then minus 1. And then clean it up. I'm going to clean it up. I'm still going to infinity. So what does that bottom one become? N is 0. Then n plus 1 there. And then x to the n. And now if you start at 0, you will create the same exact series we just had. But now your series starts at 0. So we can combine it with other series that would start at 0. All right, I think we're out of time. Well, we still have 2 minutes, but I think you're probably out of time, right? Y'all got to go? Everybody got to go?
So then that one that you told me earlier for the index change, we could just always use a shifted one?
Which one? The one where when we take the derivative it goes to 1?
Yeah.
Yeah, we could always switch it back to 0. It would just take one step for us to go back to 0.
Okay.
Yep. Homework. Make sure, I'm not going to give you any homework out of 8.6 yet. Is that 8.6? Yeah. Yeah. Make sure you get all your homework done for 8.5. The stack of papers are over here if you want them. What time is my calculus class? What semester? Fall?